Good morning, everyone. Today we are going to learn about the numerical quadrature using Newton's code formula. We will also apply this formula to find the trapezoidal rule, Simpson's 1 by 3 rule, Simpson's 3 by 8 rule, and Gödel's rule using Python. So let's go. Uh, what is the numerical quadrature? Numerical quadrature computes definite integrals approximately using numerical methods instead of exact analytical solutions. It essentially, when integrals cannot be solved analytically or are too complex. Applications including structural engineering, fluid dynamics, thermodynamics, signal processing, probability, and computational physics. Here, there are approximates integrals for evaluating function of x at equally spaced points and interpolating with polynomials. Right? Integration a to b f x dx is nearly equals to summation of coefficient into function value. The concept is equal interval spacing h equals to b minus a by n, where polynomial interpolation approximates the function between the sample and points. So we will firstly find the trapezoidal rule. It uses linear straight line approximation between consecutive points. First order Newton Cotes formula using degree 1 polynomial interpolation. Geometric interpretation calculates the sum of trapezoid area under the curve. Simple yet effective for basic numerical integration tasks. Here are the formula or here are the trapezoidal rule. Integration a to b f of x dx is nearly equal to h by 2 y0 plus yn plus 2 y1 y2 and until the yn minus 1. Now we will move toward the Simpson's 1 by 3 rule. This is a parabolic quadratic interpolation through 3 points. Second order Newton Cotes formula, degree 2 polynomial, requires even number of intervals, more accurate than trapezoidal rule for a smooth function. Weight patterns goes like 1, 4, 2, 4, 2, 4, 1. So here are the formula of Simpson's 1 by 3 rule. It goes like integration from a to b of function of x dx, which is nearly equals to the h by 3 y0 plus yn plus 4 y1 plus y3 plus y5 and plus dash plus 2 y2 y4 and y6. These are the even numbers, and in multiplication of course there are the odd numbers. You are doing that on the screen. Now we will come toward the Simpson's 3 by 8 rule. It simply says it is a cubic polynomial interpolation using 4 points. Third order Newton Cotes formula, degree 3 polynomial. It requires a number of intervals and divisible by 3, often more accurate than Simpson's 1 by 3 rule for smooth functions. Useful when interval count doesn't suit Simpson's 1 by 3. Here the formula goes like integration from a to b function of x dx nearly equals to 3x by 8 y0 plus y1 plus 3 y1 y2 y4 and y5. It does not include the divisible of 3 and plus 2 y3 y6 y9. It's the divisible of 3. Now we will see the Vidal's rule. Something misprinted here. We are saying that integration from a to b function of x dx is nearly equals to 3x by 10 y0 plus 5 y1 y2 plus 6 y3 plus y4 plus 5 y5 plus y6. It is a sixth order Newton Cotes formula using 7 points. A specific weighting pattern 1 5 1 6 1 5 1. Higher polynomial degree is superior accurate, ideal for smooth, well-behaved function. Provides order of h to the power 7 error conversion. Here you can see the graph, how it goes up to the 7 point. Now here are the comparison between the Newton Cotes methods. So here trapezoidal linear, which is degree 1 degree, and they provide order of h to the power 2 accuracy. Low complexity best for quick accuracy. Here next, Simpson's 1 by 3 rule. It is quadratic. second degree and provides order of h to the power 4 accuracy. Requires even and interval. Simpson's 3 by 8 rule. It's a cubic third degree and it also provides order of h4 accuracy. Requires n divisible by 3. Now, Vital's rule is the most and sixth order polynomial, order of 7 h to the power 7 accuracy, uses 7 points. The insights are higher polynomial degree is better accuracy for a smooth function. Increased accuracy requires more computational effort. Choice depends on functions, smoothness, and accuracy versus the cost trade-off. Simpson method offer a good balance of accuracy and efficiency. Gödel's rule provide highest accuracy when precision is critical. So here we can conclude one thing that trapezoidal is good for the fast and Beadles is good when accuracy and precision is critical. And these Simpson 1 by 3 and Simpson 3 by 8 are composite between both. Now here the formula to implement the Newton's code methods. Here we define the function fx which returns the value of fx squared. For trapezoidal, we define a function def trapezoidal where we give arguments a, b, and n. Here first we calculate b minus a by n, the difference, and then in result we put f of a plus f of b for I in range of 1 by n is equal and return a result plus 2 into my f a plus I into my h. Here it suggests that we add the first and second number here as we are gonna to see in our trapezoidal rule. Hmm. So you will see in the formula that we have to add first and last and then multiplied everything by 2. So we're doing exactly like that. Yeah. So we exactly doing that multiplying by 2 as multiplying by 2 into my f a plus I h and at results we will return h by 2 into the result. Okay. So now we it's defined for extension one third. We will also say take the same argument, calculate the difference, and addition of first and last store in the result and start the for loop. And the for loop result plus equals to 4 into my f a plus I into my h. If I is divisible by 2, I divisible by 2 else 2 into my f a plus I h. According to the condition, we will also see Simpson 1 by 3 rule. Here we have to divide 4 to the odd and 2 to the even. So we define here the condition exactly that I divisible by 2 if gives remainder then only 4 this is multiplied by 4, otherwise it will be multiplied by 2. So odd number will be multiplied by 4 and even number will be multiplied by 2, and we will return the result by multiplying h by 3 into result. Now it comes for the Simpson's 3 by 8 rule, where we also give the same argument, calculate the same difference, and store the results or store f a plus f b into the result, and start the for loop for h in range of 1 to n. Uh, Here result a plus equals to 3 into my f a plus I h if I divisible by 3. Otherwise, if anything that is not divisible by 3 multiplied by 3 or the divisible of 3 gets multiplied by 2 and return 3 into h by 8 into results. So here the Python implementation for the all the three methods. Now, now we will go to the sample output applications. Now sample output for fx equals to x square over 0, comma 4 n equals to 6. Trapezoidal is nearly equals to 21.33. Simpsons 1 by 3 is nearly equals to 21.33. Simpsons 3 by 8 is also and exactly for exactly 64 by 3. All methods converge to exact value. Real world applications like engineering uses it for stress strain analysis, beam deflection calculation, scientific computation, and physical simulation, signal processing, numerical problem, and experimental data. Now, advantages and disadvantages of these methods are it handles the difficult integrals without closed form solution. Fast and computationally efficient approximation, easy to implement in Python, adjustable accuracy by changing number of intervals. Approximation introduces truncation errors. Accuracy depends heavily on the number of intervals and poor performance on discontinuous or highly oscillatory function. Floating point round of errors can accumulate. Endpoint sensitivity may affect the accuracy. These are some advantages and disadvantages of the methods we have learned there. And with that, we conclude our video of Newton's codes formulas. So Newton codes formulas provide practical numerical integration tools that balance accuracy and computational complexity. Python enables efficient automation of these techniques for real-world applications. That's all for today. Please like, share, and subscribe. Practice and explore numerical quadrature further to master these essential computational methods. Remember, students, consistency is a key for anything. So do practice, do numericals, and learn about these methods more. Thank you. Have a nice day.